In the previous podcast, we looked at the first four combination functions, which were the sum, the difference, the product, and the quotient function. In this podcast, we'll look at the last of the composition functions, or the combination functions, which is called the composite function, f composite g, or f composed with g. Let's take a look at the definition. Definition: f composed with g of x, written f big dot g of x, is defined by f big dot g of x is f of g of x. So if you want f big dot g of x, first you have to find g of x, then you take f of that. The domain of f big dot g is the set of x's as follows. X has to be in the domain of g, that's so you can find g of x. And g of x has to be in the domain of f, that's so you can take f of g of x. Well, let's see this definition in operation. First off, though, I want to point out a difference in notation. This is the product function notation. Look at the dot. It's a small dot and it's solid and black. That means f times g. Whereas this dot is a big and empty dot, big and open. That's the difference between the composition notation and the multiplication notation. Okay, let's take a look at our first example. Suppose f of x is 2x squared plus x and g of x is 3x plus 1. What would f dot g of 3 be? Well, according to our definition, f dot g of 3 would be f of g of 3. So to figure out what that is, we have to know what g of 3 is. So I'd come up here and I look at g. And g of 3, I'd put a 3 in for x. So I'd have 3 times 3 plus 1. So that's a 10. So f of g of 3 is f of 10. Well, now we need to know what f of 10 is. Well, we could write f with empty holes. And then we could plug 10s in the empty holes, and that would give us f of 10. Well, 10 squared is 100 times 2 is 200, plus another 10, 210. Now let's do just a general f dot g without any numbers in it. Suppose it says find f dot g of x and simplify. Well, again, f dot g of x, and this is the way you'd start the problem, is equal to f of g of x. And when we went to find f with numbers, we wrote it with empty holes. So let's write it with empty holes again. It's 2x squared plus x. This time I'm going to use big empty holes because I have to get g in there. And into the empty hole, what I'm trying to take is f of g of x. So I want g of x to go in each empty hole. Well, g of x is 3x plus 1. So let's simplify this out and see what we get. We get 2 times, and if we square 3x plus 1, we get 9x squared plus 6x plus 1. And then if we add to that g of x, we get plus 3x plus 1. Well, multiplying the 2 gives us 18x squared plus 12x plus 2 plus 3x plus 1. And combining like terms gives us 18x squared. Now we have like terms here, 12x and 3x. Add them up, 15x. And we have like terms here, 2 plus 1 is 3. So that would be our f dot, or f composite g of x simplified. Let's take a look at another example. Does g dot f of x give us the same thing as f dot g of x? Well, let's try it out. In the second example, g big dot f of x would be g of f of x. And to do that, you'd want to write g with empty holes. So g was 3x plus 1, so you'd want to write 3, great big empty hole, plus 1. Great big because f has to go in there, and f was kind of complicated. F was 2x squared plus x. So that's what goes in the empty hole. Now we distribute the 3 and we get 6x squared plus 3x plus 1. And since none of those are like terms, we can't simplify. We simply box it and we're done. And notice this, f dot g and g dot f completely different. Now the next one asks for a different skill. It says rewrite the function h of x equals 2x plus 3 squared as the composite of two functions. Well, that 2x plus 3 looks like a straight line function to me, and then here's a squaring function. So those are the two functions I'm going to use. And if I was evaluating this, I'd do the 2x plus 3 on the inside and the square on the outside. So I'm going to do it like this. I'm going to say f of x is going to be the squaring function, and g of x is going to be that inner line function, and then h of x would have to be equal to f dot g of x. Let's see why that's true. If we go ahead and use the definition, f dot g of x is f of g of x. So we would want to write f with empty holes. Well, f of x was just x squared, so we'd put empty hole squared. We'd take g of x and put it in the empty hole, 2x plus 3, and there is our h of x. Now, our last example is based on a table of values. Here is basically two sets of ordered pairs defining a function f and a function g. So for the function f, when x is negative 3, f of x is 1. When x is negative 2, f of x is 3. For the function g, when x is negative 3, g of x is negative 7. When x is negative 2, g of x, or y, is negative 5. And so we're supposed to do some evaluations using this table. So let's get started. The first one wants f dot g of 5, so that's f of g of 5. So we need to know what g of 5 is, so we look up x equals 5. Well, holy moly, x equals 5 doesn't appear. That is the part of the definition that says x has to be in the domain of g. Here x is not in the domain of g, so no answer. We go on to the, or you could have said undefined. Let's take a look at the second one. It says take f dot g of negative 2. Well, that would be f of g of negative 2, and this time negative 2 is right here. It is in the domain of g, and g of negative 2 is negative 5. So this gives us f of negative 5. So now we need to know what f of negative 5 is, but holy mackerel, negative 5 is not in the domain of f. So that's the part of the definition that said, and g of x has to be in the domain of f. So again, this is undefined, or we get no answer. Now let's do a couple that we can do. The first one we'll do is f dot g of negative 1. And we get f of g of negative 1. And negative 1 is one of our domain elements for g. And g of negative 1 is negative 3. So this gives us f of negative 3. And negative 3 is a domain element for f. f of negative 3 is 1. So this is just 1. So f dot g of negative 1 was positive 1. Let's try g dot f of 2. That would be g of f of 2. And again, 2 is in the domain of f. It's down here. And f of 2 is negative 2. So this would be g of negative 2. And negative 2 is right here in the domain for g. And g of negative 2 is negative 5. So this gives us negative 5. And that completes our podcast on composition of functions.